All right, so welcome back, everybody, to week 3 or 2 or whatever week we're in. I think this is our second online session meeting. It's good that they're well attended. So Julie asked a good question, where can we find the recordings? So when you go into the Blackboard Ultra Collaborate menu, there's a 3-bar line, not when you're using the program, but when you're actually in Blackboard. And I'm going to make some video instructions on how to do it. But I was supposed to do that, but you should be able to find the recordings and download them. They've been appeared for other classes, so it should be okay. But yeah, but remember, they do take a couple hours to process. So hopefully stuff like that will be made clear. As far as lab, I will be recording the labs tomorrow and deploying them at lab time. So because we don't need to show up, I'm not all, I'm not going gung-ho on making sure you have the lab available. I'm also not really gung-ho on having it due exactly 1 week afterwards. So I'll pretty much spend tomorrow sort of recording instructions, and it's going to be lumped together. So we're going to decrease the number of lab reports. I know I said that, but I want you to hear me saying it now. And what we're going to do is basically we're going to combine charge and electric fields. So you're going to write I guess a long form lab report and tell me what you did, and what you found out. And so you'll do that. Then you'll have the DC lab report. You'll have the AC lab report, and then our last lab report will be on magnetic fields. So you'll still have a lot of activities to do, but because we're combining them, for instance, you'll have all the lab instructions for the next 2 weeks tomorrow. So it's just a little different. I know it's a little frustrating because you guys want it to be done, but honestly, I've been kind of resting to feel better from the last week or two, and I've not had as much free time as one would hope. But as I feel better, which by the end of this week I should have a lot more time. So yeah. I just need to email the students so that I don't get a call during the lab. Anyway, I hope that's clear about the lab. I'm trying to make it a little more manageable while still getting the same hands-on stuff done, if that makes sense. So so that's what that's what I'm going for, without making it too crazy. If I had to do all the lab reports that you're supposed to do, it would get too crazy on everyone's end. That being said, I probably, since with extended deadlines and everything, I probably won't get to grading the first lab report until spring break. So make sure it's turned in by the end of the week, because I'd like to grade them and let's start getting a grading time going. So hopefully that works, and we'll see how it goes. Again, we're all just trying to make it work and make sure you get what you need. Okay, so I'm gonna start. Are there any questions about the lab that anyone wants to ask? The video instructions will be on Blackboard in the same place in section B. And again, we will not actually be meeting like this for lab. So I'll probably be on my have my Skype available if you want to call my Skype during lab hours. You can, again, my Skype address is so apparently when you type in my, oh no, that's wrong. Hold on. That is wrong. I got my Gmail and everything mixed up. It's .cuny.edu. This one is, the second one is correct. Don't use the first one. That's not even an existent email address for anybody. So you'll find a Dory icon. sad Dory icon. So you can click that. That'll be me. Look up Dory the fish on the internet if you don't know what I'm talking about. That fish is my icon. Or just click the fish. It's the only one. So I want to review briefly. We want to continue our discussion about charges in electric fields. So if you remember from our previous discussion, charge can be both positive and negative, right? And if we pick any arbitrary point, let's pick this point here, we can look at the electric field at any point due to these two charges that I've drawn here. You'll notice that if you remember positive charges, the electric field, they all come out of the positive charge. Like that. And all the charges come into the negative charge like this. The fancy way of saying this is that electric field lines start on positive charges and terminate or end on negative charges. All right? So with that being said, let's look at this point. Here, if we make a charge line, we're going to extend a charge line from the plus charge, and we're going to make it go through the point here. Now, when we do that, we'll start the field line on the point and come through. Now, it's hard to show, but you can see that this is just an extension from a field line out here, right? And we have this point. And in fact, I'm going to play with the straight line feature so that it looks better. So we notice we have the line, right? Yeah. We have the line, straight line coming from the positive charge, pointing that way. And towards the negative charge, we're going to start on the dot again, and we're going to go towards the negative charge. I got to start my pencil and look at it here. Now, if you look at this, this is the electric field line to the negative charge, and right here we have the field line from the positive charge. Okay, does that make sense to everyone? If that's not clear, we got to clear that up. Does that make sense?
Repeat that one more time.
Yeah. So if you look here, I'll do it with the pencil, and I'll change colors so that it doesn't confuse. Because color changing, you all know how much I love my different color markers. So from the positive charge here, right? This is the field line. Okay. So that's E positive, and from the for the negative one, it's this field line. Okay. So what we can see here is that this one is E negative. And what we're doing is we're looking at the electric field at this point, the blue point, which I'm now using with red too. Okay? So this field line here is E plus. It comes from the positive charge. And this one comes from the negative charge. And what I hope you can see is that you basically have two vectors you need to add at a point, right? And if you're to add the electric field lines at this point, you have to add their magnitudes and their directions. So if you were going to add this and make this more formal, what you'd say is that E at the point is equal to E plus, and it's got some, it's got a vector here, plus E minus, which of course means you have to break these, you have to define an axis and break these up into components. Now if you make your axis, right, if you just choose an arbitrary axis, like so, and call this the x-axis, and this the y-axis, in this particular problem, this would equal E plus in the I-hat direction, right, plus E minus in the j-hat direction. All right, so vectors have come back to haunt us. They're very important. All right, so does that make sense? Bueller, anybody?
Wait, so that point at where it's reaching, what charge does that have?
So
Or
the point is not charged. That's a really good question. The charges exist right here where I've indicated them. Yeah? And basically what we can look at here is the field due to the charge distributions at any point. The point itself doesn't have any charge. Okay?
and what do those vector lines represent again?
The vector lines, so these lines here, so the red are not vector lines. The only vector lines are the blue. And to answer the question, we're getting to the problem above. We're just reviewing electric charges at the moment and field lines and looking at them at points. So the vector at this point, you'll notice if you follow my cursor, this field line, if you extend it, will end at the negative charge, right? And this field line here, if you draw this field, from the positive charge and extend it, it goes past right here. So you're looking at this point and you're saying, what's the electric field due to these two charges? And so basically I've drawn the field line, right? And I've said, oh, okay, they're 90 degrees apart, and I've made my own axis. However, if you make an axis on the charges and place the charges at specific places, well, then everything gets a little more complicated, right? Then E plus and E minus will both have I hat and J hat components. All right?
Got it. Thank you.
Okay. Good. All right. So I want to now delete all this and solve the problem. Okay. So now we're going to get to the problem and we're going to look at it. So there we go. So two charged particles are attached to an x-axis. Particle 1 has a charge of negative 2.0 times 10 to the minus 7th coulombs. It's at a position x equals 6 centimeters. And particle 2 has a charge of 2.0 times 10 plus 2.0 times 10 to the minus 7th coulombs, and is at a point x equals 21 centimeter. Midway between the particles, what is the net electric field in unit vector notation? Okay, so we asked to do a problem with, it was requested that we do a problem with numbers, so that's what we're going to do. All right, so if we're going to make an x-axis, let's choose everyone's favorite axis shape, which is a straight line. We'll draw that up here in red. Call that straight. Even though that's not straight, it's like, hold on, I need to select it. You know, you try and make it straight, it doesn't work. Hold on, I'm going to delete that and just make a good straight line. It's going to be easier than rotating it. There we go. All right, so we have our x-axis, and we're going to call this point 0, right? And we'll change colors. We'll put, you know, we'll try and guess what 6 looks like. So if I call this 5, 10, 15, 20, and 25, right? Let's put our charges. We'll put our blue one here at 6. So this is 6. And we'll put our purple one at 21. So 5, 10, 15, 20, and 21 is about here. So the particle is asking us to pick a field point, analyze the electric field at a point halfway between these. So first we have to figure out the displacement, right? So the displacement between here is going to be 21 minus 6, which is going to be, someone help me with 21 minus 6. 21 minus 6, 15. Good. So this length is 15, right? 15 divided by 2 is 7.5, and 7.5 plus 6 is 13.5. So if we go to 13.5, 10, this is 10, this is 15. So 13.5 would be around here, right? And let's use a different color. I'm going to Control Z that, see if that works. Nope, that does not work. I'll select that little dot here, and I'll delete the dot. I'll delete the dot. I'm going to delete these. It's taking up valuable real estate. So I'll use a gray point here. 13.5, around here-ish. You know, it's not doing it. Well, we'll leave it purple. I'm not going to go crazy. So midway between the particles, what is the electric field at this point? So this is the point of interest, okay? And that is at, so that point is at x equals 13.5 centimeters, okay? So the first thing we want to do is draw the field lines here. So we'll look back and we'll notice that Q1, the particle at 6 centimeters, is negative. So the electric field goes this way, right? And you'll notice these two distances are the same. These two distances are the same. The charge is the same, or the magnitude of the charge is the same, rather. So in essence, we have to whatchamacallit, we'll know that we have the same relative line size. So I've almost used too many colors here, but if we look at it, the yellow line, if you can look at it, starts here and is going towards the negative charge, right? Now electric fields go towards negative charges, and they start from positive charges. So when we draw the electric field from the positive charge, we're again going to get an arrow of the same size that looks like this. So we're sort of going to double up, right? And if you remember from Coulomb's law, E equals K Q over the distance squared, right? Now remember, if we're going to use K, we have to use things in meters. We have to convert to meters and coulombs and seconds, okay? We have to do that so that our units are consistent with K. But also remember, because we're going to see it soon, I do want to remind you that E also equals 1 over 4 pi epsilon naught Q over D squared. Okay? And the way we do this is we tackle it one at a time. So we can see here that, and also keep in mind this is the the magnitude, and the arrows will actually give us our direction, right? So our magnitude of E is going to be equal to, if you can see it now, you'll notice that these are actually pointing to the left, right? That makes these negative. So if you want to put your direction in there, you can say that E is equal to negative K Q1 over D minus K Q2 over D. All right? And you have to ask yourself here, even though this is x equals 13.5, this is where that 7.5 comes back in, right? So we know from our previous analysis that D, and I made mistakes here, it's supposed to be D squared. We know that D equals 7.5 centimeters. But in order to put it into our calculations, we're going to have to put this as D equals 0.075 meters. Okay, Q1 and Q2 are given, and we have to make that conversion so that we can use the value of K equals 9 times 10 to the 9th. Okay, and when we do that, we'll see that this is all in the I hat direction, and we can see that E is equal to negative K Q over D squared, where the magnitude of Q1 and Q2 is both 2, which should be obvious from the problem. So we add these the two terms here will combine, right? Because Q1, the magnitude of Q1 is equal to the magnitude of Q2. The minus signs we get from the arrows. We got to be careful with those minus signs. And then what we can do now is this is the symbol part, right? So now we can just plug in the numbers. That's equal to 9 times 10 to the 9th. And that's K times 2 times 2 times 10 to the minus 7. Over 0.075 squared. Okay, so does everyone see how the numbers get plugged into the problem?
Can you just go over it real quick?
Yeah. So again, so when we look here, we have, let me put it on the pointer. So again, let's go over each part of the problem. So the problem has a bunch of given information, right? It gives you an axis and a picture that I drew up here. And the first thing you have to do is figure out what these distances are from the point you're interested in. All right, we did that. And then what the electric field looks like at that point from each of the two charges. All right, so Q1 is negative and Q2 is positive. Okay, so the electric field at this point will go from the negative charge, will go towards the negative, right? Because all the field lines from the negative charge end on this charge. So it will be an arrow that starts at our point and goes towards the negative charge. Okay? And then for a positive charge, positive field lines start on positive charges and they go away from them. So again, by the time we get here, you can look at this arrow, we start here at our point and we go away from the positive charge. Now, you have to remember we're dealing with vectors, so we can do the magnitude, which we get here, and then we need to analyze a picture to get the direction. All right, the negative charges and positive charges do give us direction, but they give it to us separately. So we analyze the direction, and then we go we look at the magnitude. The negative and positive signs don't fix the direction of the field, because you'll notice, as we drew before, right? I want to, if you put a point here on the origin, the field will now point towards the charge because it's ending on the electric charge, right? But again, the positive charge will still be pointing the other way, and vice versa. So So we have to look at our point to get our signs. That's the first thing, but they're two separate steps. Once we do that, we can then know what direction we're going. We can say, these are both going to be negative. So we can look at, when setting up our E value, we can say, well, we have one negative line times the magnitude, right? So Q1 is from the problem, and D is what I figured out. I'm actually going to be a little more, I'll be a little less, I'll call that 1, and I'll call this one 2. Okay? And so basically, this is just plopping Coulomb's law out, right? I added the D1 and D2 to make these more explicit. And if it helps, if it's helpful on the problem, hold on, I gotta. Oh, right, that's why the pen's not working. Okay. This would be D1, and this would be D2. So the 13 centimeters, right, that's the position from the origin that we're on. So I'm going to draw that up here. This is 13.5 centimeters. All right. I thought it might have been helpful to look at it this way. It was not. So that's just me looking at everything and figuring out where everything is. Why I say it's not helpful is because the important D's you need are the distance from the point that you're looking at, where the field point you want to look at, and the charge. So here, it's D1, and for the negative charge, it's going to be this D2 value. And we use Coulomb's law, right? Before I get this gets too fancy, we use Coulomb's law to get our magnitude, right? So for charge 1, we have K as a constant, we have Q, and we have D1. And we notice it's going in the negative direction. That's where this term comes from in our equation. Okay? We do it one charge at a time. So you can almost, if it's helpful, you can almost delete everything from the first charge, all the information here, and start fresh again from the second charge, which is this positive charge, Q2. All right? Q2 will have a field over here. You'll notice it points in the negative direction. And we know that we have K, we have our Q2 value, right? Right here. And we have D2. Now, I noticed a few things here. The magnitude of Q1 is equal to the magnitude of Q2, and D1 is equal to D2. That's where all the subscripts disappeared here, because once you realize these are all the same, you can combine them, right, to get this expression. Okay? That's given in the problem. You have to read that problem. So it's -7, not 17. Did I put -17? Okay. That means the answer is because I messed up then. I see now. There. K is given. K is one of those constants, like, you know how you know G is equal to 9.1 and 9.81 meters per second squared? K is equal to 9 times 10 to the 9th, like meters squared over coulombs. Yeah. All right. So I think we're good on this problem. We all right? I'm going to add, I would say if you want to get the numbers, multiply these numbers, or hold on, oh, that's not. Multiply these numbers on your calculator, the easy numbers, right? And divide by this, and then just multiply these out by hand. And you'll get 10 to the 2. And then you can just leave that over here, right? And then you get numbers times 10 to the 2. Let me show you that next step, what I'm talking about. I would write this as equals 2 times 4. 4 times 9 is 36 over 0.075 squared, right? That's easy enough to do in the calculator. And then you have just here times 10 to the 2, right? 10 to the 9 times 10 to the minus 7 is 10 to the 2. That was poorly written, but oh, move that there. Okay, like that. So that will speed up your calculations, and it will also stop you from writing things incorrectly in your calculator, which is probably the #1 cause of error in this class. So okay. So let's move on. I think that was a good analysis of that problem, and I hope it made sense what you would plug in, where, and what it would look like in a problem. Moving on. And I was willing to, I'm happy to do that one in particular because what we're going to see is that we're going to look at a bunch of systems now where we just build the equation, and we don't, I'm not going to spend a lot of time plugging stuff in. So I don't mind doing it once. But we need to get through these, and you'll sort of see that it's recognizing which formula to look for. But what I want you to see is where the formulas come from, because when you look at a dipole, it says that it gives you the idea of an electric dipole here, and then it gives you this weird-looking formula, right? Hold on. It gives you this formula here. There's like a z cubed and a d on top. It's like, where's all coming from? So you can't hear me? Oh dear. Can anyone? Is everyone having a hard time hearing me? All right. You can hear me? Okay. Yeah, if you can't hear me, exit and come back. If I exit the yeah, exit and come back in. All right. So yeah, I would say if everyone couldn't hear me, then I'd have to exit, but that's problematic because we'd have to create a new file with the recording. So if you can't hear me, oh, I guess I should say that. If you can't hear me, it doesn't make sense. If you can't hear me, try exiting and coming back in. Or try stopping and restarting your microphone. No, that would be me that would have to stop and restart the microphone. Yeah. Okay. So this is exactly, I saw an answer here I wanted to, so Lewis, you got this huge number, right? I don't think, you might get something that big because you have, yeah, no, okay, that might be all right. That seems a little big, but if you look at the last example, you have 100 times something of the order 10 to the 1, so that's 10 to the 3, minus 10 to the minus 2. Yeah, no, your order's right. That sounds about right. But I'd express that in scientific notation if you can, when you can. So while we're waiting for people to get back in, remember we're recording, so anything should be viewable later. But you'll notice that the dipole moment looks a little different. And we want to look at and be able to derive this formula and understand where it comes from. Now, it used to be in the old exam form, so when we first started meeting, I would give you this problem and fill in the steps. And you would justify each step. I love giving that problem, but we won't be able to do that because, again, like I said, we will be switching up our tests to a Wiley Plus examination. Anyhow, so we have this, a dipole is an object that's created, I'm going to change colors, yellow bores me, that is created by a positive and negative charge, all right, of equal magnitude. So if you have something like this, say plus, plus, 3 pluses and 1 minus, this is not a dipole. All right? Not a dipole. And that's important because it's important to recognize if you're dealing with dipoles, the magnitude of the charge must be the same. Okay? And before we just accept this, let's take let's take a look at what we mean by the properties of this dipole moment and what we mean by a small distance. So I have a bigger picture that'll let us draw and in a meaningful way. So let's look at the let's look at this part of the dipole, and you'll notice we can find the electric field along the axis of the dipole. All right? If you look back at the previous equation, that's the result we'll expect. But let's take a look at the two parts of any electric problem. First is the charge distribution, which we talked about before. And you'll notice that on this, that we have this plus minus charge distribution, right, aligned like so. This will be called the dipole moment eventually. On this side of the distribution, we're closer to the positive charge, so the positive field will always be bigger than the negative field. And down here, the negative charge will always be closer than the positive charge, so the negative charge, or the electric field due to the negative charge, will always be greater. So we're going to pick an arbitrary point up here, and you'll notice that you can do it the same way we've done all the problems. We're not changing anything. We're picking a point. We're looking at the positive charge. We're drawing an electric field vector. Remember, that field vector will start at the positive and extend outward and point away from the positive charge. The negative charge, now we'll look at it for the negative charge, the field line will go towards the negative charge, right? But looking at these, we know, I want to remind you of Coulomb's law again, or at least the electric field. So E equals K Q over R squared. R squared, D squared, doesn't matter. I'm just calling it different things. So you'll notice that, by definition, the Q's will be the same, right? But if we're on this side above the positive charge, we know that R plus is shorter than R minus, right? So if you look at these two distances, this is the distance from P to the negative charge, and this is the distance R minus from the this is for the positive charge, R minus is for the negative charge. Now I want to point out that D, the distance between the charges, in order for this to work, D must be much less than R plus and R minus. Okay? So D needs to be very small compared with these distances. We've made it to scale so that it's easy to see, but I think you can see it. So what I want to do is we want to look up, or not look up, we want to derive the equation for the dipole. Okay? So when we look at this, we can say, oh, okay, or at least along the z-axis. And that's going to equal E plus, right, minus E minus. Hold on. Now again, where do my signs come from? Right? We set this way up so that the minus direction would correspond with minus, but our minus just comes from looking at this charge distribution. That's it, right? If we're looking at that, remember, this is the point of analysis. Here, E plus is positive. E minus is negative. So that's why the E at the dipole, at this point P, I'm going to change this actually to, I'm going to delete that, and I'm going to write, okay. So let's look at E plus and E minus individually. E plus is going to be equal to oh, is someone else drawing? Don't draw, because you're messing up with my stuff. You shouldn't be able to draw. I am the only moderator. So, hold on. So E plus will equal K times Q. Again, that's the absolute value. I'm just being, if it'll make you feel better, over R plus. And E minus is going to equal over R minus squared. Now, the trick to electromagnetic problems is to turn uninteresting distances into interesting distances, but this can sometimes seem harder. So so we want to be able to find this dipole along any value of z, but we're sort of stuck with these R plus and R minuses that are not helpful. So we want to rewrite R plus and R minus in terms of things that are helpful, which is this fixed distance d that you can see right here, and this arbitrary length z. All right? So let's do that very quickly here. We can see that R plus is equal to, right, z minus d over 2. Okay? That's R plus, right? If you get, oh no, wait a minute, I've somehow, so if this is z, then we're going to, yeah, so z minus d over 2 is that distance, and then R minus is going to equal z plus d over 2. Look at that a couple times until it makes sense. I'm going to show it with the pointer now. So this R plus is equal to this z is bigger than R plus, right? But if we lop off a little d over 2, then we have R plus in terms of z and d over 2. And we have R minus, it's z, but in order to get to R minus, we have to add d over 2. So that's where we get that distance. And when we look at, when we plug everything in, it's hopefully going to make some sense. So you'll notice that they have this, I want to do it here because it's cleaner. So we did these two steps sort of by hand, but now you'll notice that we have a nice algebraic expression in terms of z and d, right, for our dipole moment. And then we have to do some, but basically what happens now is we get a lot of algebra, okay? So basically, getting to this step here is you're doing some algebra and factoring. So it looks like they factor out a z squared out from the bottom, and you get this, these two terms. And now what happens is you can, hold on. You can combine the fractions, right? So basically what they do is they use a common denominator and they combine this whole thing into one expression, okay? And so you'll notice that the d over z comes in here, right? So that z comes down here and you get the z cubed. So you have your q over 2 pi epsilon naught z cubed, and you have this d over 1 minus d over 2z part. Now remember what I said before, okay? There's a criterion here. So from here you do algebra, which I'm not going to do. You do arithmetic of fractions, which again I'm not going to do. And you pull stuff out and simplify, and you can recast into this term. And then you'll notice that the criteria we had is that for the in order to be a dipole, D had to be much less than both R plus and R minus. Another way to say that is D had to be much less than Z. Okay? And if that's the case, then D over 2Z will be much less than 1. And you might be asking yourself, why does that matter? Well, in this term, if D over 2Z is much less than 1, so like say 0.1 squared is going to be 0.01. So 1 minus 0.01 is pretty much 1. And as you get smaller and smaller and smaller, this term essentially doesn't matter. And we can say that this term, right, will go to 0. And then we have this nice simple expression for the electric field of a dipole. Now, this is important to see because you'll notice with the dipole, you have two charges. Coulomb's law tells you there should be two terms, and there are, but then we do math to simplify to a more elegant and compact term. We have a resultant E field, okay? And we can simplify it even more by recognizing that by inventing this term called the dipole moment and setting it equal to QD. All right? And that simplifies it even further to give us this compact expression for the electric field of a dipole. Okay? Questions? Thoughts? Good? So remember, I'm just going to summarize this really quick. The important thing to hear is that first, we apply Coulomb's law directly to our charge distribution, right? We find we're able to, or not Coulomb's law, we're able to add field lines based on our definition of how field lines react with charged particles. We can add the fields. Then we apply Coulomb's law, right? Which gives us our fields. Oh, crap. If you're not getting any audio, I don't really know what, because everyone's hearing me, so I don't think it's on my end. I would say, you know, I'll have, he's not getting any audio and I'm answering him in audio. Let me, hold on. Where's my, oh, right. Where's my, there we go. If you still can't hear me, check your speakers to make sure they're not muted. And search for help on Blackboard. The video will be available. You can download and watch later. Okay. So, anyway, we apply Coulomb's law directly here, and that's where we get these two magnitudes. Okay? We recast the hard stuff in terms of stuff we know, interesting stuff. So this is just a substitution. This step. And then this is annoying algebra, more annoying algebra, using the dipole approximation, right? This stuff that we have here. And then we have our there are two terms for the two charges, but they can be combined into one term for the dipole. So the way to think of this is an electric field for one dipole. All right, and that's why there's one term here now. But you should keep in mind it can be derived from looking at the two charges individually. Okay? So we're going to do this actually with more distributions. Okay? And we're going to see that the calculus is going to play a little more of a role here. All right? So for instance, if we looked at this charged ring and a point above the center of the charged ring, this is a little more complicated than a dipole, right? There's now one object, one charge, but it's distributed. Okay? So you'll notice that we want to notice a few things here before we go on and look at the math, which I believe is coming up next. Hold on. Yeah, good. Okay, I wasn't crazy. So we want to look at a few things and make a few notes. All right. First, we'll notice that this ring of charge, you have to look at, if you have a distribution, you want to, the way to deal with things with a distribution is to make it simple, right? So if we have this whole circumference S of charge, well, we can't just blurt out the whole thing. We want to look at a small chunk of it and pretend it's a point charge, and then add it up continuously, thank you integration, until we can get the whole distribution of charge. So the first thing we'll do is look at the electric field due to some negative positive charge here. You'll notice the ring is positively charged, so the field line will go from this point out here at this angle theta, because you'll notice you have some angle to the axis, right? You have you make an angle theta to the axis. Your electric field will also have a corresponding angle. Now, what's interesting here is since you only have a little bit of the charge, you only have a little bit of the field. Okay? So now another thing to notice is that as you can imagine taking little different ds parts, that's what you're looking at in this figure here, you'll notice that you kind of make this cone, the symmetric cone. And what you should notice is that if we take a slice of it, that even though we have a dE coming here, there will exist some ds on the opposite side that will give us a symmetrically a symmetric dE that has the same value of theta. And so what you can note here is that the horizontal components of the electric field, right, those will cancel. The positive components, or the vertical components, will add. And the way we've defined the angle theta here, right, if we make a right triangle, we have cosine. We're interested in this version, right? That z, that we're interested in the DEZ component, right? And DEZ from our triangle will be equal to EDE. That's a z, not a 2. Cosine theta. Okay? So that's where this DE cosine theta business comes from. We have to use the tools from Physics 1 to unpack the stuff we're doing in Physics 2 to make it manageable, because things get hard really fast. Also, something to notice is that we usually are used to dealing in Coulomb's law with Q. Now, if we have a distribution here, we can have a linear charge distribution, right? Where instead of Q, we deal with DQ. I didn't like how that came out. Where instead of Q, we now have to deal with DQ. So let's rewrite Coulomb's law here in a new way that will be useful, which is that DE, right, is going to equal K dq over r squared. That's keeping it very real, but it emphasizes the fact that we're looking at differential parts, and we'll have to integrate to get the whole thing. Now let's look at some specifics for this charge distribution. All right. I want to write it above here so it makes sense again. dE equals K dq over r squared. All right? So you'll notice that dq is equal to lambda ds. Now, why does this make sense? Lambda is the linear charge density. So this is, if you make this curve small enough, it's a line, right? So the line is going to be lambda and then some ds along there, right? This little ds. So that's our dq term. K, thankfully, is constant. And then r squared is still r squared. So you'll notice we look here, we go dE equals K, or they have the 1 over 4 pi epsilon naught. This is the same, right? dq over r squared, and they replace it here to this new part here, or this new representation. Now, again, r is not super helpful, right? Every time z changes, we have to redo the problem, or r changes, we have to do the problem over again. So you'll notice we're looking at the point, we only care about the electric field along the z-axis. So we can use our right triangle, and instead of having r, we can say that r squared is equal to z squared plus r squared. Now, why do I want to write that? Because we have r squared down here at the bottom. So we don't need to take the square root and all that. We can just plug in r squared with z squared plus r squared. Okay? And this gives you this new dE part. Now, when you look here at dE cosine theta, let's look at the triangle, right? So we have dE cosine theta. We want just this component. But we can see that the triangles are kind of equivalent. So we can write that cosine theta is equal to, right? So if this is theta, it's the adjacent over the hypotenuse, z over r, or this is going to equal z times z squared plus r squared to the 1/2. All right, so you'll notice that when you plug this in, z appears up here at the top. All right, z appears up here at the top, and you'll notice that instead of having to the 1/2 times 1 down here in the exponent is 3/2. So that's where the 3/2 comes from. Now, in order to get the the whole thing integrated, to find the complete electric field from everything, we have to integrate both sides. So you'll notice they integrate over here, but you'll notice you're integrating along this path S from 0 to 2 pi r. So all this stuff actually comes out of the integral, right? Because z stays the same, r stays the same. Those aren't variables in this particular thing. We're just moving around the circle. So that creates what I like to call a very manageable integral here. Oh, no, I wanted to draw that. Right? This is a very manageable integral. From 0 to 2 pi r, it's just going to be 2 pi r. You stick it in here, and you get your expression for the charge ring distribution. Now, whenever you have to solve for the electric field along a charge distribution, you'll use this equation. Or hold on. You'll use this equation. All right? This will help. Okay? But it's important to see where this stuff comes from and realize that it's not all magic. Now, I just want to get through the disk because we're going to see it in a little less detail, and then we're going to go on break. Okay? So for a charged disk, oh, they have all the stuff. We already went through all that. For the charged disk, all right, you're going to notice that you have quite a difficult integral. All right, so you set it up in sort of the same way, the dE the same way, but let's look at the differences. So with the charged, with the charged disk, this is the easy part, right? And again, everything comes from exactly the same way. You're just taking a small chunk. The only problem is this time when you integrate, it's not so easy. And when we look here, we have dE over sort of something similar, and you'll notice dQ, because we're dealing with a solid, so we can write dQ is equal to sigma, that's the area density, right, dA, which will be equal to dr ds going around. So when we do this, or no, actually from 0 to r rather, sorry about that. So when we integrate dE, you'll notice we get that sigma z part, and you want to change this into dr d phi. So right, I'm being a little silly here. So dA equals r dr d phi, I believe. If I'm getting the Jacobian right. So when you do that, you'll find that that d theta is easy. It's just 0 to 2 pi, right? So that's going to cancel the pi and the 2 here. And that's where the sigma z over 4 epsilon naught comes from. And then you're going to be stuck with this integral. All right? And I love saying this. This is physics class. Look it up in a table. If you want to do it by hand, you can, but I expect you to just look these up in tables and get the answer. That's fine. You can do that, and you will get this equation as the electric field for a charged disk. Okay? The process is the same to get all of them, and if the integrals are easy, do them, like they are here for theta. If they're not, look them up in a table. There's no need to kill yourself doing integrals by hand. Okay, I got a bubble here. Hold on. Oh, okay, that's checking system settings. All right, so let's go on break. We'll come back at around a little after 7, and we'll get going again. I'll leave it recording. So if something comes up, I'm going to go away and get some water, and I'll be back in a little bit. Okay? But so that you can still see the chat if any good questions or things like that come up. So here I go. I'm going to go away. You all get to hear my coughing for the next 5 minutes or so. I know it's exciting. Oh. I know. Oh. I'm okay. It's just I'm recovering. It's been a kind of a rough 2 weeks. Yeah. But last week was bad.
It's just not my day. Try asking, what can I say?
What is this? Is that my phone? I've been looking for my phone all day. Oh, good. I'm glad you're feeling better, Lewis. I have a feeling. I have a feeling that the whatchamacallit, what was all that noise coming from? I'll have to figure it out later. Yeah, I don't think they test me though, because my whatchamacallit, my fever wasn't that high, but my temperature is usually only about 96 or 97. So when I get up to 99, it's a pretty bad fever for me, even though the medical community disagrees. Yeah, I know, but I was just coming off a cold, so I think that's why it was mild. I don't know. I'm feeling better. It's already run its course now. I think I'm just coughing and hacking. But I want to be fever-free for 2 weeks before I really leave without my N95 mask. Which, when you have a dust allergy, you usually have a few around. So 2 fevers during that period. That's not good. I've only had the 1 fever so far. And it lasted for about 3 days. But the frustrating thing is there's really no avoiding it. You know, all this stuff is to slow it down so that the health system isn't overwhelmed. I think that's a part of it that gets lost in the news. Oh, I'll survive. I gave lectures last week. I did okay. Let me see here. I'm just going to clean up a little of this stuff. I've got my cough drops, so I'll probably put in one of those before I lecture again. I forgot I have my handy garbage cans. But where was Siri coming from? That was weird. I have all sorts of weird stuff. Opening the windows is a challenge, Isabel. They're all old and rickety. So opening them actually isn't the challenge, it's closing them. That is the trick. So I was let me see. I was having well, I wish let's see. Oh. Oh. I was having audio. I was audio issues. I was having audio issues, and there was a browser setting. Oh, geez. I'm gonna put this over here. So, all right. Setting. When the programs. funny thing is I had this issue too when I first started this, and there was, I'm trying to tell Marcel that you could click something in the browser and it was able to enable me to hear everyone. Because I couldn't hear, don't you guys remember I couldn't hear anybody in the first lecture? Or that might have been the, no, I couldn't in the 231 class, and then I was able to fix it. Let me see here. And we'll get going in a minute. Oh, geez. Well, I think that's earned a cough drop. I'm going to need these for tonight, though. I'm going to try to go to sleep, which, if the past is any indicator, the future is not going to be easy. So, I hope Marcel fixes the audio issue, but okay. So let's find my pen, trusty pen, and let's continue. So, does everyone see that it's the same procedure? Are we okay on our distributions and how to do it? Because that's sort of what I want to point out to you. It's the same physics analysis, which is figure out what dq is, right? Write Coulomb's law down, and then integrate and get your electric field. Now, if you're wondering, must there be an easier way to get electric fields? There is. It's this exciting topic of our next chapter, Gauss's law, and we'll get to it in a minute. But sometimes Coulomb's law will be the easiest way to do things, and Gauss's law also involves integration. But hold on. Nope, that's the wrong thing. But we have, before we do that, hold on. Okay. All right, sorry about that. We'll talk about Gauss's law. There is one thing I want to do first. And so here, we'll look here at a system we'll look at pretty regularly, all right? And which is a deflecting, which is two parallel plates. Now, you'll notice that the electric field is constant between these two parallel plates. It's just going to go from the positive to the negative plate. You're oppositely charged. And we're going to look at the force of a deflective plate. And I want you to notice something that we said, we haven't said today, but we would have said last time, right? So if E is equal to KQ over r squared, right? And F is equal to K Q naught with our test charge Q over r squared, where Q is the Q without the subscript is the Q due to the electric field. We can write pretty simply that F is equal to Q naught times E. Okay? And when we look at a deflecting, something being deflected here, we can also say that F is equal to MA. And this lets us actually look at, we can say that MA is equal to QE, and we can solve for the acceleration of this charged particle. Now keep in mind what this is here. We have a charged particle from an inkjet. This is how this works. A charged particle entering an external field. So that's why we have the field by itself here, and then Q naught is the external charge interacting with the field. And we can actually find that the acceleration is equal to Q times E over M. And now that we have the acceleration, we can plug it and do physics 1 stuff. And what I mean by this in particular is we can look at the trajectory of this charged particle and solve for it analytically. Because we can relate our physics 2 stuff, the charges in the electric field, to our physics 1 stuff, and then we'll get kinematic equations and things like that with the Q's, E's, with the charges in the electric fields. So it's pretty darn useful. So we can analyze electric fields, and we can look at trajectories of charged particles with Coulomb's law, which is essentially, even though we're looking at the my cough drop is not helping. Even though we're looking at the focusing on electric fields as an application of Coulomb's law, it's still from Coulomb's law here, okay? And that lets us do all that interesting stuff. So now what we're going to do is we're going to sort of broaden our picture, and we're going to extend our discussion of electric fields and make them a little more abstract. They couldn't be abstract already. All right? So we're going to load our new file, which will stop sharing chapter 22, and we'll start sharing chapter 23.
Do we have to worry much about 22-6?
So you do, you do, because I'm going to be, remember the way the test is going to go, I'm going to be developing pools of questions, and you will get questions from chapter 22 and from the parts we covered. I won't take things from sections we didn't cover, but yeah, I'd say you could be asked something. It's fair game. I have you till 7:55, I believe. So that's when class ends. So if you have to, you know, everyone's got to do what they got to do. But you know, yeah, I'm gonna put up a practice test. Hopefully that'll help. The list of topics is basically just everything we've covered. So you'll be able to review the lectures you have on here. And like I said, from waves, I'll make that part very clear. Yeah, I'm not going to spend too much time talking about it, but because all the information is like written elsewhere, so you can just read it and see it. But basically, the test will be multiple choice questions. So to sort of answer Lewis's question, it's likely something will be drawn from this chapter, and that you'll have to solve it. So you know, you should be prepared. And I recommend you have an equation sheet. I mean, I'm at home, I can't manage it, so I'm just going to say don't feel bad if you use both sides, because the questions might be from a broader, it might be harder to figure out what's broader, but it's up to you to do that. I still haven't decided yet. It is not going to be it's not going to be next week, basically, which was the original thing. It's either going to be, it's probably going to be right after we get back from spring break, because I still have to figure out how to do it, and there's still stuff to figure out. Okay, same number of exams. Nothing new there. All right, did it load my? It did not load my file. That is not cool. First, second, and final. Yeah, so 3 total exams. Yeah, we're not changing that. Did not share my file. That makes me sad. All right. So, well, it's cumulative, right, in the way that all physics tests are cumulative. You'll have to know stuff. Stuff will be relevant from this chapter in the last chapter, but I'll only ask questions from those last chapters. So, but you will need to know information. Okay, so let's look here at Gauss's law. And in order to understand Gauss's law, we're going to have to understand a quantity called electric flux. Okay? The best way I have to describe flux is the stuff coming in is negative flux, and the stuff coming out is positive stuff. And if we're going to ask ourselves, well, what do you mean by stuff? That's a good question. I specifically mean electric field lines. Okay? So let me go on my thing here. Anyhow, I just have to, someone's asking about this class on Skype, and I have to ignore them so that we can, that was one thing I didn't foresee, is multiple things. So I'll hopefully they'll figure out that I'm actually teaching at this very second. So Gauss's law will relate the electric field at points on a closed Gaussian surface to the net charge enclosed by that surface. But we need to build up this idea of flux first. So as you can see, we have field lines, right, that are coming off this dotted object called the Gaussian surface. Now, a Gaussian surface is abstract. It is not a fixed idea. You get to pick what the Gaussian surface is. However, it is recommended that you pick something with the maximum amount of symmetry for the problem to make your life easier. So for point charges, you usually choose a sphere. All right, but for line charges, a sphere is not the most symmetric thing. A cylinder would be more symmetric, right? So, and we'll see examples of all this as we go forward. So you'll notice that we have this enclosed charge. If we double the charge, you'll notice that in our picture, the field lines increase. All right? But now you'll notice something. They're exiting the Gaussian surface. But I want you to notice a few things. One, if you zoom in close, notice the angle between the field vector and the Gaussian surface. You'll notice everywhere you look, it's 90 degrees, right? Even when you double up. And you'll also notice that inside here, we've doubled the positive charge. If we have a negative charge, you'll notice we've decreased the flux lines, right? And now they go in to the surface, not out of the surface. So our rules can be applied here looking at these Gaussian surfaces. However, as we'll see, it won't become clear until we can define flux. So we're going to see some of that definition starting in the next slide. All right. So if you look here, one thing you should note is that the electric flux is the dot product of the electric field vector. That was easy to see. And the dA vector. Now the dA vector is kind of hard to imagine. If you have a piece of paper like I have here that has some area, right? The dA vector is perpendicular to the area and always points out. So you can see as I switch the orientation, I switch my dA vector. Okay? I don't know if you can all see that, but that's the idea. Now, we're going to see this more explicitly in this slide where we can see the dA vectors are always perpendicular to the little slot that they have. Okay, but I don't want to quite look at this slide yet. We're not ready. So going back here, you can see that the two important parts are the dA vector, which if I were to draw on the circle, I'll draw it here. Oh, I almost wrote with permanent pen on my tablet. That wouldn't be good. So we can, if you notice, we can draw a dA vector. It's always perpendicular to the surface. Okay? Now, with the dA vectors, those are dA vectors, and it's easier to see here at the plane. You can see that this is the A vector, the dA vector. That's one part that you need for flux, because flux is the amount of stuff that goes through an area. Okay? That's the thing. If we're looking at electric field flux, it's the amount of electric field that goes through an area. So that will consist of the area and the electric field. And if we take any small region, the d flux here, it will be equal to E dot dA. Okay? So when we're looking here, we're going to need to integrate this equation. Let me clear that. We're going to need to look at this equation here. And we're going to need to integrate it, right, to get the total flux. All right? So you'll notice if you look at this from the deflux from a geometry point of view, you have your dA vector pointing along the x-axis, and you have your electric field vector pointing at some angle theta with respect to the x-axis. So delta phi can be E times delta A times cosine theta, the angle between them, right? That's the definition of a dot product. So in order to get the flux, the total flux, you'll have to integrate this up. This is a problem, though. This is a vector integral. And unless you've taken Calculus 3, you've probably never seen a vector integral. So we're going to keep it as simple as humanly possible. And the total flux is going to be equal to the integral E dot dA. That's just through any random area you choose. But if you have the closed surface, which is using Gauss's law, you'll have this circle here, which is that the closed surface integral is equal to E, the integral of E dot dA is the net flux through a surface. So let's talk about where each of these two integrals applies by looking at this giant surface. So you can see this closed surface here is an object. And you'll notice we've broken this complicated surface up into manageable little planes, right? So here's 1, here's 2, and here's 3. So I'm looking at each of the individual surfaces here. No, this isn't good. Is my battery dying? No. Oh, that must be, okay, good. So it seems that my mouse battery is dying. I'm going to have to deal with that. So while it seems like, so these three surfaces, yeah? Or maybe I was just over there. No? Okay. Sorry about that. These three surfaces will correspond to this integral, right? These are just total flux through these individual surfaces. However, if we integrate around the whole surface, that is the net flux through the surface here, all right? So the whole surface gives you this one, all right? Whereas each of these little ones here, 1, 2, and 3, they correspond to little bits of flux here, okay? So now as we can see here, we can sort of get a qualitative understanding of the field through, clear that, through looking at the, I need my mouse more than I let on, so I will see here, hold on. There we go. Ow. My poor mouse. There we go. Okay. So, okay, good. It was just bothering me. So, so like I said, these, we can look at these individually, or as I was about to say, and we can look at the angle between the dA element and the electric field to determine whether the flux in each particular part is negative or positive or zero. Right? So you'll notice here the angle is obtuse, it's large. And hold on, I just have to. Okay. So, we have phi less than 0 for the larger angle. For the smaller angle here, phi will be greater than 0, and here phi will be equal to 0 for this 90-degree angle. Now, interestingly, what Gauss's law will eventually show us is whether there's charge inside here. All right. And inward flux is negative, outward flux is positive, and then, of course, with the 90-degree angle, it's 0. So you really have to ask, am I exiting or entering the surface? Is really what you have to ask. You'll notice with 3 here, you're coming out. This one's going in, so it's going to be negative. I don't think the angle will. The angle might give you that, but I don't think it will. So those are the in the final, can you repeat them? How many exams will there be? Guys, it's all in the syllabus as far as the exams go. I know people are asking about that. Or Sadie, are you asking about this in particular? I think you're asking about this in particular, because that was minutes ago. Okay, so again, if we look here, we'll notice the electric field is going in. You can see it here. It's going into the surface, right? So if you're going into the surface, that's defined as negative flux, all right? You can get the magnitude with the angle, but I have a feeling it's not going to matter all that much. All students, but cosine will be negative if it's greater than 90, so you might get that part in. If you're going outside, the angle should be less than 90. As you can see here, you'll notice here, if you make this angle greater than 90, the electric field is pointing inside this with a negative flux. So yeah, it works. But you'll notice that the electric field line is coming out of the surface here, and that makes the positive or greater than 0. And here in 2, you'll notice the flux skims, but it doesn't really penetrate. The area, it's parallel to the surface or perpendicular to this dA vector. So the flux here is 0. Okay? All you have to know about flux is that it's piercing. It's either, if it's going in, it's negative. If it's coming out, it's positive. And we look at individual areas with this vector integral, and then we would look and add up all these little squares to get the net flux through the whole shape, with this being the whole shape. Don't freak out. You won't have to do anything that's difficult. At least I don't think you have to do anything that's difficult. And if you are, there's ways to do it. Okay. So I wanted us to consider a Gaussian field where the flux is negative, positive, and what the net flux through this cylinder is. Okay? So I'm going to ask you all a question. Well, I guess that question doesn't make sense. So, So what I was going to ask is basically we have to remember the net flux, which is the big one, is that phi net equals the closed surface integral of E dot dA. So how many surfaces do you see that we'd have to integrate over to get this closed surface integral? That's the question I wanted to ask. All right, so how many surfaces on the cylinder? Or do you think we can just plow through the cylinder? What do you think? Three. No, there's one whole object. This is the closed surface. But there's three individual parts you can break this up into. You can break it up into part A, B, and C, right? So we can look here, and we note that we have three surfaces. Let me circle them. So you have surface 1. This part of the cylinder is surface 2, and then surface 3. I'm going to clear all that because it's not as helpful. So again, we're looking for the net flux. It's going to be equal to closed surface integral of E dot dA. And that's going to equal the integral of E in surface A dA, right? Plus the integral of EB, or not E, sorry, there's only one electric field here. DAA let me make this make some sense. Plus the integral of E dot dA B plus the integral of E dot dA C. Okay? Now, let's take a look at each of these three integrals here. So let's look at A first. What is the angle between dA and E? For part A, right where my pointer is. What's the angle between those two? 180. Good. So that means we're going to get, when we look at this integral, it's going to be equal to E times A, whatever that area is, times cosine of 180. It's going to be minus, right? Does everyone see that? Good. Again, no problem. So the E field, this line here represents the electric field. It's a constant electric field through the cylinder, right? You'll notice it comes in here, goes out here. And then we have the electric field here. So in order to do the closed surface integral, this Gaussian surface, to look at the net field, we broke it up into three surfaces, right? A, this one here, B, this part of the Gaussian of the cylinder, and then C, right, this part here. Now you'll notice the electric field pierces and goes into the surface, so we kind of expect it to be negative, but we'll be able to prove that. And dA, remember dA is always defined as perpendicular to the area. All right, so that's our dA vector for this cylinder, and this is our electric field. And so then we get the angle. So to evaluate this integral, it's very abstract. It's just E dotted with dA. So E, I'll integrate around the whole area, whatever it is, I just get the area, right? Times cosine of the angle between them, that's from the dot product, and that's where the negative comes from. Okay, does that make sense? Good. Now, this part has the potential to be very difficult. However, you'll notice that dA, whichever way it points, however, wherever you are on the cylinder, you can move this little thing all the way around if you'd like, will always be perpendicular to the electric field, right? The electric field is constant. So when we look here, we know that the cosine of theta of 0, the cosine of 0 is no, the cosine of 90, sorry. The cosine of 0 is 1. We're not looking at 0 degrees. The cosine of 90 is 0, right? So that makes this integral go to 0. Okay? So here we have minus EA. I'll write that. Here we have 0. And so the whole contribution to the flux of this large side goes away. Okay? Now, right, cosine 90 is 0. I'm getting there. So when we look here at our third integral, right, this is only because of the way the field is orientated. So we have a field and we've drawn a cylindrical Gaussian surface, and we're looking at the flux of our surface through this given field. Okay? Now if we look at part C, right, what's the angle between the electric field and dA? It's 0. Good. So when we do that, we can see that this will be equal to E, A, and then that'll just be positive, right? So now we want to add everything. From each term, we have minus EA plus 0 plus EA. And now you'll see why we didn't need to specify anything or pick any numbers, because it doesn't matter what the numbers are or what we do. These cancel, and the whole thing equals 0. So we get that the net flux is equal to 0. Now we'll see in a minute this shouldn't be surprising, because the net flux of any shape, you could draw any shape you want and the net flux would be 0. In order for the net flux not to be 0, it has to enclose a charge. And if you'd like, you can see some more details of this. This is in nice detail here. I'll leave it up paused for about 10 seconds so that you can pause it when you watch the video and read through it in detail, but this is just the work we just did. Okay? And we're moving on. So now when we get to Gauss's law, we can also define flux, all right, the flux of an enclosed charge. I like to write it like this. The flux of some enclosed charge is equal to Q in the charge enclosed over epsilon naught. All right, you'll notice not K, but epsilon naught. This is where it pays off if you've stuck with epsilon naughts instead of Ks. So if we have something enclosed, we can solve for the phi here, and by equating these two, our previous equation, remember that the flux F net, the net flux, is equal to the closed surface integral of E dot dA, and that's also going to be equal to Q enclosed over epsilon naught, and you can rewrite it to solve for Q enclosed this way. Now, don't be fooled. This can get real complicated real fast, and sometimes, remember, Q enclosed of its point charges can be easy, and you just have Q enclosed. But sometimes you can have the integral of lambda ds around a line. You can have the double integral of sigma dx dy, or this could be an area vector integral, or this could even be a triple integral, or I'm just going to write a volume integral, rho dv. Okay, so the charge can get pretty complicated pretty fast, and carrying out those integrals is not very difficult. But you should be aware of how ugly this can get quite quickly. But now what you can do is you can see the picture here, which I tried not to write on. So you'll notice that if the charge enclosed, even if there's charge enclosed, oh crap, right? And you add up the charges, if you add them up and they're equal and you get 0, even though you still have the flux lines, you'll still have just as much coming in as going out, and your net flux will be 0. All right? So one of the interesting consequences of this is that if you're inside a conductor, right? If you have a charge distribution or a shape and you're inside it, like this, like say you're in a sphere. Say you're inside a sphere and all your charges are on the surface. Remember, charges usually migrate to the surface, whether they're positive or negative, it doesn't matter. If you look for the electric field inside, much like we found before, Gauss's law says that you're not encircling any charge. If Q is 0, right? If Q is 0, your electric field's going to be 0, and that's it. So the E field inside a conductor or charged material is 0. I mean, Gauss's law gives us that result right away. But we can use Gauss's law, right, to solve somewhat more difficult or problems and get simple solutions that Coulomb's law might not have been able to help with. So let's go forward and see that. I'm not sure what's going. Oh, okay. Oh, I see what they want to do here, and I want to do that too. Then I see what they're doing. Okay. So let's look at each of these breakdown surfaces. So you'll notice through surface 1, you're enclosing a positive charge. So the net flux will be positive, and you can just write it into Gauss's law, have that Q enclosed. The same thing with surface 2. This will be a negative flux because everything's going in, right? And it's surrounding a negative charge. And you can see that with S2. You'll notice with S3, there is no enclosed charge. I'm pointing at it here. With S3, there's no enclosed charge. Therefore, the flux must be 0. And if you look at the whole thing, the total charge is 0, right? Because +1 plus -1 is equal to 0. So through S4, there's no net charge enclosed. Therefore, the flux is 0. That was more useful than I thought. So if we look at this, again, we said that none of the excess charge will be inside the conductor. So if we look at this here, you'll notice that the charge inside the conductor will be 0, and this is a semi-infinite where we're saying this is thick enough that we don't go out the opposite side. So all the charges will stay on this surface, and you'll notice that the electric field is just sigma over epsilon naught, but you might wonder, well, how in the world do we get that? So let's use Gauss's law and derive this very quickly. So you'll notice we draw a Gaussian surface, right? And you'll notice we only know that we have one side of the surface, yeah, that's going to contribute, because we already just did our cylinder analysis. We know this edge is a 90-degree angle or perpendicular to this A vector, right, to the field, or the field will always be perpendicular to that A vector, so it won't contribute. So let's just use our simple form of Gauss's law. Let's write here. We have, and always write Gauss's law correctly, because when you start writing it incorrectly, it goes caca. And this is going to equal epsilon naught times Q. So that's the place we start. Now this equals sigma dot, or this equals the integral of sigma dot dA. Okay, because that's the total enclosed charge. So if we have a sheet it's going to be sigma times r dotted with our total enclosed area. And the sigma is going to be constant. Basically, what we've done is looked at something that could be variable and seen it as a constant part and an area part. So when we do this, we get that this will equal sigma times the area, right? And on the other side of the equation, we can see this will equal epsilon naught times E times the area as well. You'll notice the areas cancel, and you just solve for E. And that equals sigma over epsilon naught. And you can see where Gauss's law very cleanly gets you this electric field. All right? So let's see how things happen as things become more terrible. Right? So now we're going to look at the electric field for a line charge. Right? And you'll notice with the line charge, it's positively charged. There's only going to be flux going through this solid side of the cylinder. Now, don't be afraid to think of the area of that, right? The area of that cylinder is going to be 2 pi r times h. This area here. And if you think about that, that makes sense. 2 pi r is just a little bit. If you multiply it by h, you get that whole surface area. Now, you'll also know that with the line charge, the electric field is going to come out as indicated here. Right? And so when we do that, you'll notice this time the tops are not going to matter, right? Those are going to be the dA vectors are perpendicular to the electric field for the top. So we can know that though the top and the bottom will contribute 0. And if you look here, you have that your flux is equal to EA cosine theta, right? A we just got here, that's where the 2 pi RH comes from. Theta, we know they're going to be parallel, so that'll be cosine theta. So we have on one side E equals 2 pi RH on one side, and on the other side, even though this is an infinite line, we have that Q becomes lambda H. Right? They missed this part here, so let me write it down. We have that Q enclosed equals the linear charge density times the height of the charge. That's in there. It's pretty simple, right? If you want to be really formal about it, you could write it's the line integral of lambda dH, but I think you get the point. So then you can set this side, right, equal to this side, and you'll notice the h's cancel out here, right? The h's cancel, and if you solve for E, you get a nice clean equation for the electric field of a line charge. Now, who likes this better than Coulomb's law? All right, I've got one. I like it much better than Coulomb's law. Coulomb's law is a real pain in the rear, but Gauss's law can get difficult when symmetry breaks down, and sometimes when symmetry breaks down, Coulomb's law will then become easier. So you have to keep that in mind. All right. Now, if we have planar symmetry, I want you to notice if we have a sheet where we have where it extends to both sides. If the sheet is thin, this is a non-conducting sheet, then you'll notice that the charge, right, there'll be contributions on both ends. Oh, and you won't notice because I'm not pointing, on both ends of the sheet. So now we have two faces to look at, but you'll notice the electric field points in the same direction as dA in both cases. This is a little counterintuitive because it seems like it's the opposite and they're pointing in opposite directions, but we only care about this integral and then this integral. And when we do this integral, just like before, we'll get a positive EA term. However, when we do this integral, the angle between them is 0, so we also get a positive contribution from the integral. All right, so e times a. And then again, q enclosed is just going to be equal to sigma dA. You do that integral, and you get sigma times a. And you'll notice the a's cancel, and you get that the electric field is half what it was for our one side of the conductor. And that might seem counterintuitive, but in a way, it's not, because our previous example, right, cut this whole side off and all the charges were on this surface. If you make it a two-sided thing, you lose about half your charge, right? So now all of a sudden, you have to consider the electric field. If you're one at a time, you're losing half of it, right? So on either side, it will be half of what it originally was. And that's where you get this sigma over 2 epsilon naught. I know the math can seem weird, but it works. And Gauss's law, as we've learned it here, we're going to see that this is the first of the 4 Maxwell's equations that we'll learn. All right? So this will play a large role in putting everything together. It's a big, big equation. Okay. So let's see here. All right. So this would be a good place. This will be the last thing we'll cover. The parallel plates like this are going to be very important for what we look at here. Now you'll notice that we have 2 parallel plates here, right? And these look a lot like what we just saw. But I want you to notice, suppose we arrange the plates close to each other, and since they're close to each other with opposite charges, all the charges, surface charges, will migrate to these surfaces. So if you look here, let's make some sense of this. Take these 2 non-conducting plates, right? They're charged plates, whatever. The charges don't move. That's what non-conducting means, right? Or the conducting plates. So the charges are free to move around. Now, if the charges are free to move around, if you put these plates close enough together, these positives are going to want to line up with these negatives. So they'll all line up on this side of the conductor and leave this side charge-free. There's no charge over here. The electric field goes to 0. Same thing happens here. And you'll notice you get this nice, it seems like, well, these charges should go every which way. But if you look at this, and we'll see this time and time again, the vertical parts will cancel out. There will always be one point to cancel out here on the other side. So, and what we'll see is that the only parts that will not cancel out are these straight across electric field components. Okay? And so what you'll notice is that if you look at both of these, the electric field here should be 2 sigma 1 over 2 sigma 1 over 2. Well, let me show you what I'm trying to look at here, because I don't think they've done a good job here. So you have here, if you remember, sigma 1 over 2 epsilon naught here, and sigma, through here in this region, right? And if you put these close enough together, now you're going to have 2 sigma 1. So you still have E is equal to sigma over 2 epsilon naught. But now with you're doubling the plate, you're doubling here 2 sigma 1, and now you get sigma over epsilon naught as your electric field. All right, using Gauss's law to derive both of them. And this will be very, very important as we talk about parallel plate capacitors and other such things. That's it for tonight. We will meet again. Again, you'll have your lab. Again, lab will be due. It won't be due next. What you're assigned tomorrow will not be due a week from tomorrow. It will be due probably 2 weeks from tomorrow, and or after spring break, basically. And what you're going to do is you will you'll have a charge-based simulation and a you'll have a charge-based simulation and a electric field activities to do. And you'll have to do all of those, and then you'll sort of write. I'm calling it almost you do the long form lab report, but don't kill yourself to worry about how long it actually is. I wanted to take a picture of attendance. All right, I need to get my. Don't go away yet. I just need to take a quick screenshot of the attendance with my iPad because I can't find my phone, and then you can go. Don't go yet. Hold on. All right. I am back. All right. Okay. Yeah, because you're going to sort of write what you did for procedure even too. So, use those long forms, but just use the instructions. It shouldn't be too bad. Don't kill yourself trying to make it 30 or 40 pages. Just do the best you can, including screenshots and graphics. Again, it won't be due for 2 weeks, so we'll have some time to talk about it. If you need help, this is for tomorrow. Right, I'm not going to be sort of doing these kinds of things for lab. I'm just going to post the lab and have you work on it. And if you don't have time to work on it, you have the assigned time to work on it, but you have as long as you need to work on the simulations. And I'm available via Skype and other things. You can work with each other if you want. I don't mind. If you want to set up a Zoom meeting or something like that, or a Skype meeting, yeah, go for it. Sure. That's fine. The simulations are free on FET. Yeah, they will be. Yeah, absolutely. Yeah, you will not have to pay for anything. So, all right. So I got the picture of the attendance. We should be okay. And yeah, that's good. All right. Have a good day, everyone. You'll hear from me. You'll get an announcement on Blackboard, but I will see you all tomorrow, or not tomorrow, but Thursday. All right? You're welcome. And now I need to find my phone, so I'm going to hide my video so that you don't have to look at me embarrassingly looking at my phone. Where's that thing? Hey, Siri. All right. Oh, hold on. And what to call. You're all welcome. I'm just getting the thank yous. Yeah, you can. I have a few Jesus. I have a few Skype calls coming in, so maybe give it a couple minutes because I have another one. I'll be available for a little bit, but yeah. And all right, I'm going to stop the recording now.